Hello and welcome everyone to today's tutorial. So I think these are just as many people that would join. We just have like 4 members today. This is our last tutorial for the course. Before we begin, any questions regarding the previous content covered in the previous classes or the assignments? Yes.
Sir, calculating beta, sir, because I
Okay.
found it difficult. Yes, sir.
Beta in linear regression. Beta.
That hypothesis power, one minus the power of the test.
Oh, okay.
That
Okay.
part, sir.
Okay, we'll try and do that again.
This will be the last session, last class, sir.
Yeah, because we just have eight weeks course, no?
Okay,
So
sir.
this is the last
Okay.
week in that. I think your exam is soon. I didn't check the date.
Okay, sir.
Maybe I'll just post a link to the beta. Okay.
Okay, sir.
Yeah. Uh, but yeah. Anything else? Hmm? Okay. So we'll start with just giving a broad overview of what you did in the previous week. You covered mainly three topics: t-test, chi-square test, and ANOVA. So we have already done the t-test in some tutorial. I think the last tutorial itself. No, we did the t-test, or just before that. Somewhere we did where we are doing hypothesis testing for two groups. We did a two independent sample t-test there. Then this week you covered chi-square test and ANOVA. ANOVA is an extension of t-test when you apply the statistical test over many groups. When you want to check whether across groups is there a difference or not, and when the group size is more, the groups number of groups is more than two, you start using an ANOVA. Okay. So before we go to ANOVA, let's talk about chi-square distributions. Now, what are chi-square distributions? Now, if you were to take a normal distribution and just take some value out of it, take one value out of it, and you square that value, and you do this, so you have, say, you have 10 different normal distributions, and from each normal distribution, you take a value, you square it, and then add all these values. The distribution of such values, the sums, when you add the squares, the distribution of these sums of squares will be a chi-square distribution. Yeah, did you follow that? So what chi-square distribution is the distribution of sums of squares of values that are derived from normal distributions. Okay, and it is you need only one parameter to define a chi-square distribution, and that is k. Okay, k could be here could be the number of normal distributions you sample from to get those sums of squares. Okay, any questions here? We won't go into the PDF of a chi-square distribution. It's not very important. But what is important is you need to know the mean and variance of chi-square distributions. The mean of a chi-square distribution is k, and the variance is 2k. You can solve this analytically if you integrate and do it, but we won't do it because it's not part of this course. Why do we use chi-square distributions? Now, chi-square distributions are good to compare, say, variances, or because variance itself, what is variance? It's the sum of squared differences, right, from the mean. So that also follows a chi-square distribution. So to compare variances, chi-square distributions is good, or to just compare any given curves or functions, okay, whether they are similar or not. So it's also known as a goodness of test fit. A chi-square test is also known as a goodness of fit test. We'll just do an example here for a chi-square test. Now, suppose you were given a population variance, and so you happen to suppose you're given a sample variance, and you want to compare it to some expected population variance. Okay, suppose I go out into the field and again, our favorite variable is height of individuals. So I go and sample say 30 individuals in a population, and my sample variance is say something S. Now I want to see whether my sample variance is different or same from my population variance. Say my population variance is sigma. So to do those comparisons, you do a chi-square test. How do you do that? This is the formula. It's n minus 1 s square divided by sigma square, where s is your sample variance and sigma is your sample standard deviation, and sigma is your population standard deviation. So if your null hypothesis is s equals sigma, then substituting those values, you have to do this chi-square test. So chi-square is n minus s square by sigma square. You get a value of 76. What do you do after getting a value of 76? You go look up a table of chi-square distributions and probabilities. So the table looks something like this. So how many degrees of freedom we have? So I didn't specify the n. N is 20 here. So how many degrees of freedom do we have for this chi-square distribution? Anyone? I've written it here. It's 19, no?
Sir, your screen is not.
Oh, sorry. You should have asked me to share my screen. Oh, sorry. I've been talking from the screen the whole time. So sorry. Entire screen. What was I saying? So yeah, this is how chi-square distribution looks like. You got me when I said the mean is k and variance is 2k, right? And what chi-square distributions are, right? Any doubts there as to what you mean by chi-square distribution? The chi-square distribution is important to understand the F distribution. So the ratio of two chi-square distribution gives you an F square F distribution, and F distributions are used in your ANOVA test. Okay, so anything to do with variances, you use a chi-square distribution. The distribution of variances itself follows a chi-square distribution. Okay, so suppose and chi-square distributions are used to do a chi-square test. For example, if you have, so this is the formula for a chi-square test. It's n minus 1 into s square by divided by sigma square, where s is your sample variance and sigma is your population variance. Now, if you want to test this null hypothesis that your sample variance is equal to your population variance, okay, you use this formula. Let's do an example. Suppose your sample standard deviation is 4 and your population standard deviation is 2, and you have a sample size of 20. Then the chi-square value is nothing but just you just need to fill in values into this formula here. So it's 20 minus 1 into 4 square divided by sigma population standard deviation squared. So that comes out to be 76. Now, how do you know whether this is significant or not, whether they are different or not? You do a two-tail, for a two-tailed chi-square distribution, you look up a table, like how we did in our t-test and all. So this is for chi-square distribution two-tail. Uh, One second. Yeah. So we have 19 degrees of freedom, no? Because the sample size is 20, so degrees of freedom is 19. And then for an alpha value of 0.05, my so what is this? Look up the left is not. Yeah. So it's 30.144. So my value has to be greater than 30.144 for the test to be significant. What is our chi-square value? 76. So that's much greater than 30.14. So you reject the null hypothesis that S and sigma are the same. Okay. So here you say that your sample variance is different from your population variance. Yeah, that is what it is. Is that okay for a chi-square test for the example? Yes or a no?
Yes, sir. Will they be giving the chi-square table and T table in the exam, sir? How do we
You
do it, sir?
have to, yeah, yeah. You should. I think you will be allowed. Otherwise, you can't memorize that table. Come on.
Yes, sir.
So either there or you can use Excel. I don't know the function for chi-squared, but for example, for a t-test in Excel equals t dist 2t for a two-tailed test. Okay, I put in
Okay, sir.
my the array I am interested in and degrees of freedom. Say say the t value that I got was some 4 and degrees of freedom is 2. So I get my p value from there. Okay. So for a given p value of 4 with 2 degrees of freedom, I got my p value which was 0.05. So you have to just look up these tables. One way to understand what a function does in Excel is you type equal to and you type t dist. Okay, it gives you a description of what this function is available for. Okay, returns the student. See, you get this returns the student's t test. Suppose you do this, okay? You do a double click, and when you click on this link like this, it actually tells you what that function does. For example, this thing returns a two-tailed student's t distribution. It's used in hypothesis testing, okay? And it tells you what the input is and what the output is, okay? And then you can do a one tail, two tail, and things like that. This is for a two tail. Okay, one tail will be just one t, and then you have to again specify the values. Okay,
Sir, regarding T test, I have a doubt, sir.
yeah.
Uh, Sir has mentioned in his video that it measures only the upper tail. What is the meaning, sir? Upper tail of that distribution.
Upper tail for one tailed. So right or left tail, no? So if you look at a T distribution, so let's do, I'll just show you this. Two tail T test versus one tail. Let's look at an image of that. Okay. So this is what it is. One tail T test is say you just want to measure whether you're less than say this is your null hypothesis. Okay, you want to test whether your sample is greater than something or lesser than something, you do a one tail t-test. Okay, so you're checking whether your sample is greater than some critical value here. So you just do a left tail t-test.
Okay, sir.
Okay,
Yes.
versus if you want to check whether it's different from the mean itself, then you have to go this side and that side. Like imagine your population is somewhere here. Okay, and
Okay,
now
sir.
you're trying to see, now here you're trying to see whether it's less than your actual mean. So your population distribution will be here like this. Imagine a hump here on the left of that. Okay, here
Okay, sir.
you're trying to see whether it's just different from your population, so it could be on this side or that side. So then you do a
Okay, sir.
two-tailed test to see if it's equal to your null hypothesis. You do a two-tailed. If to check if it's greater or lesser, then you do a one-tailed, and that depends on whether you're on a left tail or a right tail. You do alpha or 1 minus alpha by 2 statistical test.
Okay,
Okay,
sir. Okay, sir.
did you get
Thank you, sir.
that?
Yes, sir.
So there it becomes alpha by 2, whereas for a two tail it's just alpha. Okay, okay, next we come to ANOVA. Before we come to ANOVA, what is an ANOVA trying to do? Anyone? Or what does, yeah, any model try to do? It tries to fit a line to some data, right? Yeah, any model. Yeah, so the line is what is predicted by the model, and these dots are the actual data, and it's trying to fit the line in the best way possible to the data. Okay, ANOVA also does that, and when it does that, you get something known as sum of squares of total, sum of squares of regression, and sum of residual squares. Okay, Now, what is central? What is the basic ANOVA theorem? It is this: SST equals SSR plus SSE. Okay, SST is your total sums of squares. What is that? Now, suppose you have data points like this. This red dashed line here is the mean of all your y's. Okay, so you have x and a y. The mean of all your y's is this dashed line. Now, for each point, if I want to calculate the distance from this dashed line to the point itself, that is your sum of squares total. Okay. In other terms, your sum of square total is nothing but yi minus y bar the whole square and sum of that. Okay, can you see this? It's a little small. Maybe I'll try and make it big. Okay, this is very central to ANOVA. Okay, so this is your total sums of squares. Okay, it's yi is your data point minus y bar, which is the mean of your y square, and you add all of that, you get SSYY. That is your SST actually, total sums of square. Now, what is sums of squares of regression? It is same y bar minus y predicted. What is your predicted? Any point on that line which is in line with the data point. For example, my data point is here, but my predicted value for that data point is on this line. The length of this or the distance of this predicted point from your mean, which is yi predicted, that is the value predicted for the ith x value, minus y bar. Okay, you square that and you do this for all the points and you add all of those, you get what is known as sums of square of regression. In other terms, this is your variance explained. Okay, it's called SSR. What is SSR? It is this SS square xy by SSXX, where it is basically that distance. It's written in a formula form, but graphically it is this distance. And you have to square and add all of those distances for each data point. For example, for this data point, the distance is from this from the mean to the dashed line. For this data point here, it is the distance from here to the uh, dashed line, from the mean to the dashed line. Okay, that is your sums of squared regression. Sums of squared error is the distance from the line to the data point itself. For example, this length of orange arrow here. Okay, you have to get the square of that and add all of those. That's a sums of squared residual. This is the variance that is not explained by the model. Now, what do I mean by this? Now, when you try and fit a line to any set of data points, your variance can be partitioned into variance explained and variance unexplained. Your SSR is some measure of that variance explained. Okay, SSR by SST is exactly the percentage of variance explained. Okay, so variance explained, if I write variance explained is SSR by SST, which is also your R square. Okay, R squared. This is very important. Variance unexplained is nothing but unexplained is 1 minus R square, which is 1 minus SSR by SST. Okay. Now, to see whether your model is significant or not, what you do is you calculate something known as the F statistic. Okay, which is equal to SS mean SSR, which is SSR divided by its degrees of freedom, which is K here, or K is the, or maybe I'll just write it as P minus 1, where P is the number of parameters you have, or K, let's write this as K. K is the number of groups you have, divided by variance unexplained, that is SSE, in this divided by degrees of freedom, which is nothing but number of yeah. Okay, So this is your F statistic. In an ANOVA, you calculate this. So then you check. I'll try and make this bigger. So everyone is understanding what is happening here. What ANOVA does is it partitions your variance into variance that can be explained and unexplained. And it also calculates F statistic, that is, it's SSR by SSE. In some terms, it's a ratio of variance explained by total variance. Okay. Sorry, this is SSY. Yeah, yeah. So it's some measure of your SSR by SSE. That is your variance explained by an unexplained. In some, it's a rough ratio of that. Okay. And the formula is nothing but this. This is your F statistic formula. SSR by K minus 1 by the SSE by N minus K. This is nothing but your means MSR divided by MSE. Mean square of your thing by mean square of error. Okay. And then you have to find the critical value for and compare your F value with F of uh, K minus 1 and N minus P, N minus K degrees of freedom. Okay. Yeah. Under some H naught. Your H naught could be for different H naughts, right? Your significance level could be different. Okay. Did everyone get what we are doing? So these are formulas. Okay, total variation is SSY is given by x minus x bar the whole square into y minus y bar the whole square, and that's the shortcut formula for that is this, and SSX and SSY. If you have these three terms and you have x bar and y bar, you can calculate everything. Okay, for example, you can calculate total variation, which is SSYY, explained variation, which is SSR given by, don't you don't have to know the derivation how this is equal to this, okay, but let's note this down somewhere. And this is your unexplained variation, which is SSY minus this, right? This is nothing but SSR. SSY minus SSR is your SSE. Note that your basic ANOVA theorem is this, where SST is equal to SSR plus SSE. Okay, this is your basic ANOVA theorem. Using this, you get all the other values. Okay, for example, you get unexplained variation and things like that. Let's do an example. Before that, any doubts with ANOVA? What ANOVA does? It tries to fit a line to your data and tries to calculate your variation that is explained and unexplained, and then does an F statistic, okay, which is given by these formulas. Okay. And any questions? Any questions? Hello.
Yeah.
Any questions till now? What ANOVA is?
No, sir.
Let's do an example, okay, ANOVA. Suppose you are given a data set, okay?
So ANOVA can be done for two groups or minimum three groups, sir?
Three or more, or two, even two you can do an ANOVA. So t-test is a special case of ANOVA.
Okay.
Okay. Yeah. So drug, say suppose you use three drugs, okay, on patients, and you try and see the reduction in glucose levels. Okay. Now suppose the reduction in glucose levels is given by these values 2, 5, 1, 7, 3, whatever. The units can be arbitrary, say millimoles per deciliter or something like that. Okay, these are the reductions. And you want to see whether these drugs are different or not. They are behaving differently or not. Okay. So for data like this, you use an ANOVA. One basic assumption of ANOVA is your residual should be normally distributed. Okay. What do I mean by that? When you plot, I told you about this thing, right? This here. So when you calculate your y predicted minus these, so the sums of squares of residuals. So these distances, these orange lines, the distribution of these orange lines should be normal. Okay. So that is known as normality, that these residuals should be normally distributed. Both for ANOVA and t-test, this assumption should hold. Otherwise, you can't do an ANOVA or a t-test. You'll have to use some non-parametric test. So these are ANOVA, t-test, and all are known as parametric tests because they, I mean, you use theoretical distributions as which to compare. For example, in an ANOVA, you are using comparisons based on chi-square distributions and things like that. And chi-square distribution has a parameter k. Okay. In a t-square distribution, you are comparing again two distributions which are normal. Okay, so you have to have some underlying assumptions of data to use these tests. The most basic assumption is that your residuals are normally distributed. Only then you can use a t-test or an ANOVA. Okay, you can't use it on say data which is not whose residuals are not normally distributed. Okay. So for that you have to use tests like Shapiro-Wilkins test and things like that, which are not discussed in the course, but it's important because if you get real data, first you have to do these tests, then do the ANOVA and things like that. You can't use the ANOVA t-test directly. Okay. Now let's do this example. So let's calculate our three most important values. Okay. Mm, so calculation. Your SSYY is nothing but, what is your SSYY? Tell me, anyone? It's Y. What is your SSYY? Can you, or yeah, it's this distance, no? Your Y bar minus uh, yi, this entire, the length of this red line, your total variation. Okay, not variance. I'm calling variation because variance is you need to divide it by n minus one, and yeah, that gives you the variance. But this is just variation, or simply it's SSYY, and it's given by this formula. That's sigma yi square divided minus sigma yi the whole square divided by n. Okay, so let's do that here. So what is your yi? Let's do it on Excel actually. So you need to sum all your, so I need to take the square of this, all yi's. Okay. So I take the square of all, I'm just doing this calculation here. Okay, this is, okay. So this is your, and you take the sum of this entire thing, it's 279. So equals, so what is this? What have I calculated? I've done sigma yi squared. So I've squared the yi's and added them. Okay. Minus, now I have to just add all my, is equal to just add my yi's. I'm just doing all this calculation because it's 59 and then square this. square this, it's 3481, and then I have to divide this by what? What should I divide this by? N, right? Where N is your number of samples. How many samples do we have? We have 5 3s are 15. So 34 equals 3481 divided by 50. Okay, it's 232. Okay, this is my SSYY. Did everyone get this? It's 232 point something, let's be exact.
Yes, sir.
232.0. So if I take the, so you just have to know these formula to do that. Okay, always remember these three formulae here. If you know these three things, and simple, you just from there you can calculate everything else. Okay, so equals on that minus this is 46.9, 46.933. uh, let's write that there. Okay, now what is our SSXX? It's nothing but sigma xi square. Oh, we have categorical variables here. Okay, that means you cannot straight away do this. One second. Hmm. Yeah. Okay. I think my example is wrong here because these are categorical variables and my x is not, these are for continuous x's. Okay. So I'll do this table in another way. I'll use my R. Do you see the problem here that has happened? I cannot calculate my Sx, or maybe we'll just try and do that. ANOVA for categorical. How do I calculate Sx? Let's try and see. How do I do it for? Okay, I'm not very sure of. One second. Mm, 1 second. I'll just get back in 5 minutes. I think I've messed up with the question. Just give me 1 minute. Yeah. Okay. So what we will do is it's a little different, and we have not done ANOVA with categorical variables, the derivation, the calculations for all our variance, explain, unexplained, and things like that. We have done it for continuous data. Okay, so that means our x is also continuous. So what we'll do is we'll just put drug uh, concentration. We'll change the question. Okay, and effect. Okay, now let this be a set of random values.
Screen not visible, sir.
Yeah, I'll do it. Okay, just give me some time. Yeah, I'm almost there. Okay, I'll just share my screen again. I'll share my screen. Okay, I've changed the question slightly. The reason being we haven't done in the course how to calculate our SXY, SSX and all when we have categorical data. Okay, so we won't deal with that, but you can still do an ANOVA. Okay, with categorical data. Okay, it's just that the calculations are slightly different as to how to calculate uh, what you call how to calculate the ANOVA values. Okay, suppose now this is just a very simple way, a simple problem where you are given drug concentrations and you want to see the effect that those drug concentrations have in reducing glucose levels, and these are the reductions effect. Okay, reduction in glucose level. Okay, uh, now you have to calculate whether drug concentration has effect on reducing glucose level. So then you calculate your SS. Again, you have to calculate all these things. I'll do that here. Okay. So this is my equals. I'll just take the square of that. Or can I? Okay, sums of the eight. Okay, we have an Excel thing. So sums of. So this is your X values. Okay. This is the sum of your square of X values, and this is sum of these values divided by how many values do we have? Okay, okay. Now what I've done is this is suppose your X and this is your Y. Okay, your SSYY is 207. Okay, minus this. So this is nothing but sum of all your Y values divide square of that. You take the square of that. Okay, and divided by what's this, sum of a2. Okay, by sums of square divided by 9. You have 9 samples. Okay, for this data set your XX is 126 minus 100. Okay, 126 minus 100. What is 126? It's just sigma xi squared. Okay, and 100 is sigma xi the whole square divided by n, and similarly this is 26, and then similarly for SYY it's 207 minus 169 minus 169, which is how much is that? It is 170, 38. Okay, so this is 38. Our SXY is nothing but sigma XIYI. So the our SXY is let's multiply these two values. Sorry, but to calculate our SXY, need to multiply this into this. Okay, equals, and then sum them up. So what is that? It's this. So if you look at our SXY thing, it's sigma XI minus sigma X into sigma Y by N. Okay. So we have calculated sigma XI. Now what we have to do is, so what is sigma X? It is just the sum of all our X values. Okay. Similarly, our sigma Y is the sum of all our Y values, and this is this into this divided by what? 9. Why 9? Because uh, that's a sample size. Okay, so this quantity. So XI YI is the sum of that is 134 minus 130. One second. SXY is 134 minus 130 is equal to 4. Okay. Now we have got all three values. What is our variance explained, or R square, or variance explained, SSR, that is variation explained, is nothing but, what is it? It's SXY squared divided by SX from here. Okay, SSXY squared by SXX. Okay, so that is nothing but 4 squared divided by 26. So 16 by 26 is, what is 16 by 26? Anyone? Let's do it in Excel. It's 0.61. Okay. Similarly, our SS, have I made some calculation mistake is what I'm looking at. This is sigma XI and let's do this first. Okay, yeah. So okay, so that's our SSR. Our SSE is SSYY minus this entire thing. So it's 38 minus 0.61. So that's nothing but 37.39. Okay, and then our variance, how many degrees of freedom do we have for so our mean of SSR is nothing but, it's we just have one factor, no, so it's n minus k, sorry, just k. So that is nothing but 1 second. Okay, so SSR is nothing but your mean SSR is nothing but SSR divided by 1, because we just have 1 degree of freedom for SSR. So that's nothing but 0.61 divided by 1 is 1. So that's your mean SSR. Mean SSE is nothing but uh, your SSE divided by degrees of freedom, and that will be n minus 2, right? How many? Our n is 9 here, so 9 minus 2 is 7. So n 9 minus 2 is equal to SSE is what? 7.39, 37.39. Okay, 37.39 divided by 7, which is equal to 1. That's 5.34. Okay. Now your F statistic is F is equal to mean SSR by mean SSE. That's 0.61 divided by 5.34. It'll give you a very low value. So if I do this divided by 0.11. Okay. And you have to compare this with F statistic of 1,7 degrees of freedom. Okay, let's look up your F table. Okay, F table will have two parameters. Okay, your degrees in your residual and your degrees in your explained. Okay, so numerator is 1. Can we look this up? For your alpha equals 0.05, so 1 comma 7, so it's 5.59. Okay, your F critical is 5.59 for to reject your null hypothesis. So f of 1 comma 7 is 5.59, is it? Yeah. So the value that we got is 0.11, okay, which is much lesser than F critical. Okay, so that means we do not reject the null hypothesis. Okay, this is at for alpha less than 0.05 under this alpha. Okay. So did everyone get this? So this is how you do an ANOVA to accept or reject a null hypothesis. So what we did was actually a linear regression using ANOVA. Okay. Why we did a linear regression? Because this is continuous and these formulas are for continuous distributions. For categorical, you have to do something different, which I don't know. We didn't cover it in the course also, but you can still do an ANOVA when you have categorical variables. For example, if instead of drug concentration, I had different kinds of drugs itself, A, B, C, things like that. Okay, you can still do an effect of you can still do an ANOVA. We did it here just for continuous, X is continuous and Y is also continuous. Okay, this is how we calculate all the variables. Your F statistic is nothing but ratio of this by this, and if I do that, it comes out to be 0.11, which is less than 5.59. So your F always has two parameters: degrees of freedom in the numerator by degrees of freedom in the denominator. Here in our numerator, our degrees of freedom was 1. Okay, how is it 1? Because we have so just one group, just one set of one kind of x values, or just one group. The other way to do that is just p minus 1, where p is your number of parameters. For a linear regression, you have two parameters, beta naught and beta 1. Okay, so that's 2 minus 1 is 1, and for denominator, it's n minus 2. Okay, for a linear regression. Okay, so that's how you get for f1 comma 7, and under 0.05 alpha you get 5.59 as a critical, which is much greater than 0.11 that we got. So we do not reject, we fail to reject the null hypothesis. Okay, so these kind of calculations will be asked in the exam for ANOVA. Okay, so always remember the formulas for SYY, SSX, SXX, and uh, SXY. Okay, from that you can get your F statistic. You just have to then calculate mean SSR, mean SSE, and calculate your F statistic and compare it with your critical F value. Okay, is that all right? Did everyone understand how we did this ANOVA? You have to use these formulae here. Okay, the actual formula is this. This simplifies to this formula. Okay, anyone having questions how we did this? Yeah, anyone? Hello?
I have question for a different thing.
Yeah.
There is a evaluation of assignment 4 actually.
Violation of assignment 4, but anything with, before we move on there, can we do anything like with respect to this class, ANOVA and chi-square and t-test?
No, this is clear now.
So ANOVA is important, okay? I solid step by step. I'll upload the video also. For continuous x and continuous y, for discrete x, there are formula in Excel that do it. The actual algebra is a little difficult for categorical. Okay.
Yes.
Okay. Assignment 4, you said.
Now there, question number 2 is marked wrong over there.
Yeah, I think we did that somewhere.
Yeah, but the correct marking is not there.
A card is drawn, find the value of getting a jack, knowing that the card is black. Okay. I don't remember. So, what's the answer for this? Or I have to work it out? Sorry, fourth question you said, no?
1.20.
Fourth question, okay.
Second question.
Second question only.
G.
So,
1.23 is
find the probability of getting a jack knowing the card is black. Okay, you know the card is black, and then it is how many you can have at most in a card of 52 or 26 black cards, and 2 by 26. So it's 1 by 13 is the answer.
yes, yes.
Okay, I just write to them, yeah?
Okay.
Okay. Oh, well, yeah, it's 1 by 13. Anything else?
Just a marking issue in
Okay,
assignment
I'll
fifth
just
there.
write to them. I'll write to them. I don't have a lot of power over this because I don't
Yes,
set the assignment or the solutions to the assignment, but I'll write to them.
yes. You tell them.
Yeah.
Thank you.
Okay. Anything else? So please do the ANOVA. It's important. Do some problems on ANOVA. Yeah. I'll upload for someone asked me. I'll just upload the link
Yes,
uh,
sir.
for just a video that is maybe I'll do it quickly now only so that
Okay, sir.
it's a very
Thank you, sir.
good, yeah. He does it very detailed and he does it from a very first principle basis. Yeah. Okay. So think it's this one.
True value of the population.
Yeah.
The sample mean X.
So I'll just share this link. Don't worry, beta power of a test is not. Yeah. Okay. I shared the link. Anything else?
Where will you share, sir?
So I have shared it in the chat box here. You can just.
Okay, sir.
So this is a good video. And then do examples. Anything else? Yes, Arun?
So week 7 assignment, 7th question, sir.
Week 7th
Seventh question.
assignment, 7th question. That was last week, no?
Yeah. I'm unable to get the answer, sir.
Recent study on BMI was done with 40
BMI, yeah.
who claim to engage in a variety of mean body mass index for the.
Even I couldn't get, sir. I just left it.
Okay, so mean of S1 and S2. So mean is given. So you do a t-test, okay, for a 2-sample t-test. So it's sigma 1 minus sigma 2 divided by S1 by n, root of S1 by n plus S2 by n, okay. So we'll do a 2-sample t-test. There are online calculators for this, but in the exam you'll have to work it out, okay. So the formula is
Is it T plus, sir, for that?
Use Z statistics, sir.
Z statistics only.
Two population means two population means.
I mean, it approximate to a t-test. Okay, because Z statistic also, it's the same formula.
Sorry, I use the formula x1 bar minus x2 bar minus d0 divided by square root of s1 square by n1 plus s2 square by n1 n2. But I couldn't get the answer, sir.
No, what have you done? You have to just use x1 minus x2 by your whatever formula is.
Yes, sir.
Okay. So
I'm getting 9.20 something, but it is not there, sir.
So this is what you use, no? For let's do. Yeah, 2 independent means. Yeah. So this is the formula you used, right?
Can you share on the screen, sir?
You can't see the screen?
No, sir.
No, sir.
Oh, okay.
And the 9th question is based on the power, sir, which also I couldn't do.
Power question. Okay. This we did, no? You look at the video and do this again. Okay.
Okay, sir.
I won't. Yeah. You just have to calculate your Z set and see whether it's greater than what critical it is. Like, and do 1 minus beta of that. 1 minus whatever probability of that. So it's type 2 error. You have to calculate, is that greater than, so 0.1 is what? Yeah. So this 0.1 difference, so x1 minus x2 is that difference is 0.1, that's already given. Log unit. Everything is in log, no? Yeah.
Yeah, everything is in log.
Yeah. So for this difference, divided by your s by root n, calculate z of that, and z greater than, you need to calculate probability of the z value of the got greater than your critical z. So critical z you get from this 0.05. Okay.
Okay.
For for 100, you'll know what your Z critical is. 100 samples. Okay, and
Yes.
you calculate probability of Z greater than Z critical. Okay, and then that's your power. Look at that
Okay.
video again. I'll use
Okay.
this one. I'll just use. So this is the formula. This is nothing but this
The sample is
55.
100, no, sir.
Huh?
Sir, for sample size 100, the previous power of study that we have asked, no, so madam asked one question.
Yeah, yeah.
That is sample size 100. So for degree of freedom will be 99, sir.
For
Degree of freedom to calculate.
degree of freedom here, actually here it will be 99. Yeah, n minus 1.
The table, they don't have that 99.
Yeah, yeah. No, no. Here actually you don't. You just use your 100 to calculate your S by N, your standard error. Okay,
Yes.
and then you compare it with your Z critical. Z critical should be 1.96 for alpha equals 0.05.
Okay, sir.
Okay,
Yes.
so Z greater than 1.96 and you do that.
So is it enough to calculate beta or 1 minus beta? For power means beta or 1 minus beta?
Power is 1 minus beta.
Okay, sir.
Okay.
For calculating that beta, we have to watch the video which you have posted, sir. How to calculate
Yeah,
beta?
yeah.
Okay, sir.
Okay. Now what I have to do is do this t-test. I can just click the mean. One second. I just. Uh, it's not a good calculator. I want a calculator which just do sample test. Choose type, do sample. Yeah. Okay. There's a sample size of what was the sample sizes of your cricket? So can you tell me about the cricket things? What is the sample size?
24, sir.
And what was the mean?
Mean 27.75.
And standard deviation?
2.64.
And second sample size for the other sports?
40. Multi-sport, 40, sir.
40.
So here, which one will be one? This cricket only will be one, no, sir? Okay.
So second sample size is 40, is it?
Yes, sir.
And what was the mean?
22.41.
And what is the sample size standard deviation?
1.27.
1.2?
27.
27. Okay.
Even I got 9.20, sir, but it is not present in the answer.
Okay. You got 9.20 and it's not in the answer.
Yes, sir.
Uh, okay, maybe I'll just try. What was the answer then?
Don't know, sir. Not at
Okay. Maybe I'll
tomorrow,
write
sir.
to them regarding this also. I didn't do the calculation.
Okay, sir.
So actually, you have to say what is your T
So I have doubt below
critical
which, sir,
for what is your
peak.
T critical for how many degrees of freedom? Wait, T T critical T table for 0.05. How many degrees of freedom we have in total? We have
So 0.01 is given, sir. Alpha 0.01 it is given, sir.
alpha 0.01 is it? Okay. P value. So this is for just 0.05. Okay, we'll test for t equals 0.01. So we got this as 9.28, no? So t table, let's see.
Sir, I have a basic doubt. Is it T test or Z test, sir, for this
So the formula is the same.
formula, sir? Yes, sir.
So the Z table we have to see or T table we have to see, sir?
T table, yeah.
If you use Z formula, why can't we see Z table, sir?
No, it's the same, no? The z dot t table here. So what we have calculated is the t statistic. So z statistic formula is also the z test for two samples.
See, answer everything is given as Z statistics, sir.
Okay, okay.
Z is equal to like that is given, sir.
Okay. Oh, it's in Z, is it?
Yes, sir.
One second. So this is, did you use this formula?
Yes, sir. This formula only, but mu1 minus mu2 is 0. It use, sir.
V1 minus mu2 is 0.
Minus D0, there is one option, no, sir. I don't know. That is what I use, sir.
This is the actual formula, but we are unable to apply this, sir. The values they are given is not sufficient.
Yeah. Because if for Z test, no, you need to know the population means also.
In one of the videos, sir had told like uh, for testing the null hypothesis, you can have it as 0 like that, sir.
Okay.
That is what D0, D naught.
Okay.
Minus D naught.
And then when you calculated, what did you get as your Z value when you do that formula?
I got 9.20, sir.
So 9, and what is the Z value for Z table? Let's look at the Z table then. So alpha is 0.01.
It's one tail or two tail, tail. It's a two tail or one tail, sir.
Depends on whether they have asked greater than or just different. No. Okay. So you got 9.28, which means it's much greater than
0.2007. 9.20.
So the cricket players have a higher BMI than the multi-sport men.
For one tail should be 2.58, sir. That value critical should be 2.58.
Yeah.
Yes.
There's a
Yes.
typo there.
2.58. It's given as
Here they are given
2.38. Yes.
2.38.
Yeah, so
Yes,
you have to
sir.
do
That
a
is
one
another
tail
error.
test and 2.58. Okay, it's not minus 2.58 also. It's 2.58 and your value is greater than that. Actually, under P equals 0.05. So 0.005 we need to check. Z table. Hey, but here they have given alpha equals 0.01 and here they have given. It's not, the options are not framed correctly, is what I think. So you got minus 2.9.8 or plus 9.8? Did you do cricket minus this thing?
Yes, sir. I did cricket minus multi-sport, sir.
And you got a positive
No,
value,
no. Yes, sir. I did cricket minus multi-sport and I didn't get negative, sir. Positive only.
Yeah, you should get
9 point.
positive. Actually, this thing, no, it's greater, so it's 9. Actually it should be reject. What is the Z statistic, Z table for 0.05? Want to see Z table? One tailed for 0.0. 1 second, yeah. One tail Z test. Yeah, it was for 0.005. So 0.005 is not there only here. Yeah, we have to go much lower, I guess. Okay. But they have asked for alpha. I don't understand why.
I've asked for alpha 0.01, sir.
0.01, yeah. So that is this only.
Yes, sir.
One tail. It's minus 0.23. Or right tail will be plus 0.23. Okay. Sorry. So 0.01. Yeah. This is one tailed, is it? This is a different table. I don't know why it's given. Yeah. 0.01 for what degrees of freedom they haven't given. But yeah. So I think the answer to that, it's not framed correctly, the answer. But so it should be, sorry, where is that? You reject the null hypothesis. Oh, I lost that page. Yeah. It was this, no? So it's actually, it should be this, the last option, but it's not, the option is not framed correctly. Okay. This should be some 9 point something. It's not written properly only. Okay, and it's greater than 2.38 is what should be written, and p less than 0.05. It's not framed correctly, but this should be the answer, and the value should be different here. Yeah.
Yes, sir.
So that is there. Yeah. So this is last as week 7, question 7, no, and the other one was week 4, question 2. I'll make a note. Yeah, I will write to them regarding this. Okay.
Yes, sir.
Okay. Anything else? Yeah, these questions sometimes they have typos and it becomes difficult since it's just an objective thing. Yeah. Okay. Okay. Anything else?
Nothing, sir.
Okay.
Thank you, sir.
Okay. Okay. Thank you. Thank you. Thank you for
Thank you very much, sir.
course. Yeah. Thanks a lot. Bye.